everyone. We're going to start chapter 5, which is all about something called stereoisomerism. So what does that mean? It's a big word. Basically, down below, you can see two molecules, and you'll notice that they are mirror images of each other. We have this COOH group on top. We have some hydrogens, some hydroxyl groups, and methyl groups. So they're mirror images. However, if we tried to overlay these two molecules, they wouldn't overlap with each other. So for example, let's say we tried to rotate these bonds so that the hydrogen and the OH group are on the other side. And then if we try to shift it back and overlap it with the first molecule, it doesn't work. And this is similar to your right and left hand. So if you hold your hands up facing each other, they are mirror images of each other. But if you try to flip one of your hands and have it match perfectly with your other hand, that doesn't work, right? Your thumbs are on opposite sides, your pinkies are on opposite sides, and so that's something called a stereoisomer. So let's talk a little bit more about that, but first we have to go over a term called chirality. So chirality, this word comes from the Greek word, I can't pronounce this, but it's K-H-E-I-R, Keir, I think, or care. And this stands for handedness, essentially. Oops, close parentheses. All right. So, similar to your hands, molecules can be mirror images of each other, but they might not necessarily overlap perfectly with each other. So let's look at an example. I'm going to draw a molecule here where we have a carbon bonded to bromine, chlorine, and fluorine, as well as a hydrogen. So the fluorine is coming out of the paper towards us, and the hydrogen is behind the paper. Now let's draw the mirror image of this molecule. Okay, so we have mirror images here. Now let's try to overlap the two molecules on top of each other. So let's move our bonds on the mirror image around. So we're going to move them counterclockwise. So when we do this, the chlorine is going to shift over to the left-hand side. The hydrogen was a dash bond, so it was behind the plane, but when we turn it, now it's going to come out in front of the plane. And fluorine is going to be behind the plane. All right, so now if we tried to overlap that with our original molecule, could we overlap them? No, the fluorine does not line up with our original fluorine, and the hydrogen doesn't line up with the original hydrogen. So they're actually flipped. So these are non-superimposable molecules. All right, so let's take some notes. Just going to make some room here. So the molecules up above are mirror images, but they cannot overlap. Oops. Overlap. So a molecule is chiral when it is non-superimposable on its mirror image. Okay, so the two molecules we drew up above are, again, mirror images of each other, but they are non-superimposable. So that means they are chiral molecules. So they're similar to a left hand and a right hand. And there are many molecules that exhibit chirality. For instance, if you're taking biology, you've probably learned about enzymes. Enzymes have chirality. So enzymes need a very specific conformation of a molecule in order to function. Additionally, amino acids, some amino acids are chiral, so they have a left hand and a right hand. And there are many other examples as well. So this is a really important part of chemistry, is understanding when a molecule is chiral and when it is not chiral. So let's do some practice problems. Let's see if we can identify whether a molecule is chiral or not chiral, also called achiral. All right, so example 1. We have a 5-membered ring and 2 wedges. Number 2, we have that same 5-membered ring, but this time one of the wedges is a dash. And number 3, we have an alkene. So that's a hydrocarbon with a double bond. Now, let's actually go through and name these molecules first before we decide whether they are chiral or achiral. So starting with the first molecule, how would we name that molecule? So it does have a ring, which means that the ring is the parent, right? So how many carbons are in that ring? 5. So that would be pentane. But it's in a ring, so we add cyclo in front of it. And then our substituents are both methyl groups. And remember, we want to make sure that our substituents have the lowest numbers possible. So we would number these 1 and 2. So this would be 1,2-dimethyl cyclopentane. Okay, but isn't the second molecule also 1,2-dimethyl cyclopentane? So how do we make sure that they're different? Well, you'll notice that in molecule 1, we have 2 wedges, right? And they're both pointing up towards us. So they're both on the same side, which means that they're cis to each other. So we would add cis in front of our name. Cis 1,2-dimethyl cyclopentane. Okay, so what about molecule number 2? What is the term for opposite sides? Trans. So this one would be trans 1,2-dimethyl dimethyl cyclopentane. All right, so that's how we tell the difference between those two molecules. We use the terms cis and trans. All right, and then don't worry about naming our last molecule. We haven't learned how to name alkenes yet, but we will in the future, so don't worry. All right, so now that we've named our molecules, I would like you to draw the mirror images of each molecule, and then try to determine if you can overlap the mirror images. So if you can overlap the images, then they are not chiral. If you cannot overlap the images, then they are chiral. So try to determine if these are chiral or achiral. So you might want to pause the video and try this first, and then we'll go over it together. All right, so let's try to determine if these molecules are chiral or achiral. So let's draw the mirror image of molecule 1, although I can tell I already didn't give myself enough room. There we go. So we have a wedge on the side and a wedge on top. Okay, so can we superimpose these two molecules? Now remember, these molecules are normally freely rotating in space. So you could rotate them like a clock, so clockwise or counterclockwise. You could flip them like a pancake, so just turn them over, or like a piece of paper, turning that over. So you can rotate these in any way you need to in order to determine if they overlap. So let's turn this molecule clockwise, or yeah, clockwise. I was trying to remember, wait, which way does a clock turn? All right, so we'll move the first wedge to the top and the other wedge to the side. So now does that overlap with the first molecule? Yes. All right, so that means that these two molecules do overlap, which means they're actually the same molecule, so they're identical. So the other term there is they are superimposable. So does this mean that they are chiral or achiral? So they are not chiral, so they are achiral. All right, what about molecule 2? So let's draw the mirror image. All right. So is there any way that we can rotate that molecule in order to superimpose it on the first one? Well, what if we try what we tried before? Let's rotate it clockwise. So the dash moves on top, the wedge moves over to the right. Can we superimpose that molecule on the first one? No, they don't match very well. What if we flip it like a pancake? So if we just flip it over, well, let's keep track of our carbons. So we'll label carbon 1 and carbon 2. So again, we're flipping this over like a piece of paper. So the dash at carbon 1 is behind the plane, But when we flip it over, that's going to point above the plane. So the dash becomes a wedge. Similarly, the wedge, which is pointing up, is going to point down when we flip that over. Well, that just looks like that molecule, which we already know doesn't overlap with the original one, right? Okay, so that means that these are non-superimposable. So they're non-superimposable mirror images. So would this molecule be chiral or achiral? Chiral. Oops. All right. Now for the last molecule, let's draw the mirror image. Are these superimposable or non-superimposable? Superimposable. In fact, they're identical, right? Oh, I keep hitting the next button. So or is this molecule chiral or achiral? Achiral. So these are not chiral. So we don't have a left hand and a right hand. We just have two left hands or two right hands, depending on how you want to think about it. Okay. So just a tip for figuring out whether these molecules are chiral or achiral, you can look for an internal plane of symmetry. So if a molecule has an internal plane of symmetry, it is not chiral, so it's achiral. So let's redraw those molecules that we just looked at. Let's see. So our second one had a wedge and a dash, and then we've got our alkene. Okay, so a plane of symmetry means that you almost have a mirror image down the middle of the molecule. So for instance, in our first molecule, there's symmetry down the middle. So if your molecule does have a plane of symmetry, it is achiral, and we already determined that this molecule is achiral. What about our second molecule? Are there any planes of symmetry? No, I don't see any. If we try to draw one down the middle like we did before, we have a wedge on one side and a dash on the other. So those are not symmetrical. So that means that this is chiral. And then what about our very last molecule? Is there a plane of symmetry? Yes. So it's down the middle. So that is achiral or not chiral. All right, so this was just kind of an introduction to chirality. Next time we're going to talk about something called a stereocenter. So I will see you then.